Hello, my Algebra 2 students. Welcome to the new way of doing class. All right, today we're going to be looking at lesson 1.2, and that deals with sinusoidal graphs. All right, so last unit we spent talking about trig functions and learning how to quantify them, mostly using the unit circle. Now what we're going to do is we're going to start translating all those numbers to actual graphs, okay? And the very first thing that I want you to have a grasp of is the standard form of a sinusoidal function, which is right here. Now, notice how I rewrote it by hand down here and I color coded it. So A is in red, B is in blue, C is in green, and D is in orange. That's because they each have very specific things that they affect. Okay? A affects something called the amplitude, and we are going to talk about that today. All right, the amplitude. And in layman's terms, basically, that's how tall a sinusoidal graph gets, or how tall the mountains are and how deep the valleys are. And that will make perfect sense whenever we start looking at a graph. All right, B. B is the thing on a graph that affects something called the period. Okay? Now, the period is the time, or more specifically in terms of a graph, the distance that it takes the function to return back to its starting position. Okay, and there's going to be some caveats that you need to be aware of with that, but we'll get to that later. All right, C deals primarily with horizontal transformations. Okay, so basically moving the equation to the right or to the left. And of course, being the ever inquisitive, pattern-driven students that you are, if C has to do with horizontal transformation, D, of course, deals with vertical transformation. Okay, and that's just moving things up or down. All right, that's the general gist of these equations. Now, it's not that we're actually going to get to them today, but I wanted you to see this because it is important information. The big guys we're going to get to today are amplitude and period. All right, and of those two, we are actually going to start talking about period. So let's go ahead to our first definition and problem. All right, period is the time, or in this case, the distance. It takes the function, and that should be function, sorry, not functions. My, can't even edit appropriately. To return to the original point, going the original direction. All right, now that's a very important distinction, okay? Because check out this graph here. Let's say we start at the origin. Let's say we start off at 0, 0, okay? And we're traveling along this graph. When we come here to this point, did we get back to 0? Yes, we did get back to 0. All right, and when I say 0, I mean in terms of the y value being equal to 0. Okay? But we're not in the same position based on the direction we're going. Whenever we were at 0, we had a positive slope, right? M was positive. We were traveling up. When we're here at 3.14, which by the way, we are at pi, x equals pi in this case, the slope is negative. We are tending down. Okay, so what I mean by the period, it's the time or the distance that it takes the function to return to the original y value with the original slope direction. All right, so we're trying to return to y equals 0 where the slope is positive. So we continue following our graph and we end up here at 6.28 and change. There's where y equals 0, and of course our slope is positive because we are moving up again. Now, Remember, these functions are useful for measuring all kinds of cyclical activity, right? The moon revolves around the earth, give or take every 28 days. The earth revolves around the sun, give or take every 365.25 days. Okay? The tides, we have high tide twice a day, low tide twice a day because they follow cyclical motions, being pulled by the gravity of the moon, actually. Okay, so there are hundreds of applications for this in the real world. Now, let's get to a standard formula. You'll most certainly see this Greek letter used to measure period. This is omega. All right. That is the Greek letter omega, and that is, I do believe, lowercase omega. Now, the general formula for the period is the regular period of a sinusoidal function divided by the absolute value of b. Okay, and remember we said above b was that coefficient in front of the x term. All right. Now, that takes on a couple different forms because sine and cosine are very similar functions, and we will get to looking at that later. All right. Their standard period is 2 pi. All right. And this graph actually was a sine of x, just regular old sine of x. All right. So when we got here to this point, all right, we were actually at x equals 6.28 and change, which we know as 2 pi. Okay? So the regular period of sine and cosine are 2 pi. It takes 2 pi, I want to say revolutions, because when I think of this, I'm thinking of going around the unit circle. All right? So it takes a revolution of 2 pi, which means going around the circle one time, and that gets me back to the beginning, right? Well, whenever I actually plot that out using the unit circle value as my y value and the x value, or the measurement of my angle as the x value, I get a graph that looks like this. Okay? And like I said, b will change things. So if I put a 2 in front of this graph, and I go ahead and do the math, I'm going to end up with a period of pi. Okay? If I have a 4 in front of the b, or a coefficient of 4, it's actually going to end up being pi over 2. Right? And this guy is about equal to 3.14. Which means it will return back to the original position in half the time. And this guy is approximately equal to 1.57, which means right about here, or a quarter of the time of the original, it will take to get back to its original position. All right. Tangent's a strange bird when it comes to graphing. Its regular period is pi. Okay. It occurs twice as often as sine and cosine. Okay. Now, we have found the period graphically. I've also given you the ability to find it algebraically. On your quiz, they're going to ask you to find it graphically. So, what is the period of this sinusoidal function? Why don't you go ahead and press pause on the video and calculate that given what we already know. All right, so we want to answer this question. What is the period of this sinusoidal function? Well, right here is the starting point, and at 0, it starts at y equals 0. Okay, and the slope is, of course, positive. So I want to find where that happens again. I come over here to 2. I have the y equals 0 part, but remember the slope is negative, so I need to keep on going around to the next time y equals 0. Which is right here at 4. And in this case, the slope is positive, just like the original. So my period is from 0 to 4. So 4 minus 0, which of course is 4, and that equals the period. All right? It's that simple, guys. Let's see if you can figure out this one. What is the period of this sinusoidal function? Go ahead and press pause on the video, calculate that, and then press play to see the answer. All right, this sinusoidal function has a very short period. Okay, we start here once again at 0. And by the way, you do not always start at 0. Okay, we could actually start here at 2. All right, the slope as it approaches is positive, and y equals 2. And we follow that until we get back to y equals 2 again. All right. It's just a little more difficult to calculate that because we don't have that on a standard x value. I do believe that is 1.5 though, but I wouldn't bet on that. I would stick with this method. All right, so our slope is positive here, right? We're going to go up, down, we come across it again, but remember the slope is negative. It has to meet both criteria. So we go past and come all the way up here to 1. At 1, y is 0 and the slope is positive. So, obviously 1 minus 0 gives me a period of 1. Remember, the period changes how squished the graph is, or how compressed the spring gets. So if your graph looks like this, now based on how you view it, of course, on your graphing utility, but that would have a very large period compared to a graph that looked like this, which would have a very short period. And that's exactly what we have going on here. This purple graph was a short period, shorter than this green graph, which had a larger period.